Welcome back, my little calc babies, to our topic of integration by parts. So we're in chapter 8, 8.2 in the Larson textbook, and the topic is integration by parts. So what is it? What we're gonna tackle this a couple different ways. This is a very interesting and useful technique. So first, let me start with when would you use it. Then I'll kind of jump into how I'll show you the nuts and bolts of how it works. Then we'll practice some. So the idea is when you have, so for example, if you follow me off over here to the left, when you have integrands, right? When you have integrands that are products, so notice we have an x squared multiplied by a sine of 2x, or an x squared multiplied by an ln x. So when you have integrands that are products, right, of algebraic transcendental functions, then the integration by parts technique is extremely useful for getting this integral. And by transcendental functions, I just simply mean functions that transcend algebra, right? So ln x is a transcendental function. Sine of x is a transcendental function. I mean, if you should fact check me, but if you really want to go farther, what am I talking about? It just means you can't use basic operations to express that function as a finite sequence. Now, what we want to do, like the goal is to show where this derives from, right? Where do we get this from? Because it can easily escape you. So take a look at what I have written here. So the product rule from derivatives. So this is right out of Calc 1. Remember, if you have two functions, now I know that you are used to seeing f of x and g of x, and seeing the product rule written as f prime and g prime. I do understand that. So I didn't use f and I did not use g purposefully because I'm trying to mirror the same notation that we're going to use in this new technique. So, but wait a minute here. Don't let that pass you by. This is a product. We have u, which is a function of x, right? So that's a u of x. And this is v is also a function of x, so that's v of x. So taking a look to the right, this makes perfect sense. You would have u prime times v plus u times v prime, right? That is the product rule of derivatives. But yet, what we have is, if you kind of, again, you'll have to follow me off to the left of the screen for an example. So when you're setting up the integral of x squared ln x, notice that you have the product. In its current form, you could say that currently the integral looks like the left side of this equation, right? Because you know what I'm talking about. The integrands are your derivatives, right? Because just like addition is the inverse operation of subtraction, we have integration and derivatives are inverse operations. So what we place inside the integral is in fact a derivative. And that's what we have. So the derivative d of x multiplied, the derivative with respect to x of u times x. The goal of this process is, look, this is really complicated if you try to tackle it the way it sits right now. So what we're going to do is we're going to see if we can break this up into parts. Notice the term integration by parts. We're going to break it up into the parts of a derivative. And we're going to see if that integration process runs a little bit smoother. Now, how do we do that? Right? So how do we get to this formula in Theorem 8.1? Well, it doesn't take much. You maybe maybe need a quarter of a cup of coffee in you, and you can follow me through this. This is very simple. We're just gonna, if you integrate both sides of this function, right? I should say both sides of this equation with respect to x. What do you have? Right, it's getting a little bit cluttered. Let me get rid of some of these zeros. So if you integrate both sides of this function with respect of this equation, I should say, with respect to x, what's left? Well, let's look at the left side because this is really easy. If you integrate a derivative, right? If I multiply by 2 and then divide by 2, well, you're going to cancel out. So you're simply left with the product of u and x. So the only thing left on the left side of the equation is the product. Now, I think I said u and x, but I should have said u and v, the product of u and v. Okay. And as of right now, I'm just going to rewrite the right-hand side of the equation. Right? Because we got just a little bit more work to do to make sense of this. Okay. So how do we work this out? Well, first off, let's notice a really easy trick. So we have u prime times v plus u times v prime. Now that is that's a sum, and we can break up our integral so that it is now the sum of two different integrals. So that would be u prime times v dx plus u times v prime dx. Okay, now that was an easy step. So it's still not looking like the theorem 8.1 above. So what else do we need to do? Well, I want to show you what's going to happen. I'm going to come off to the left to do this. But I'm going to show you what's going to happen to this v dx and this actually, let me make sure I got everything in the right spots here. I'll tell you, this is why I don't teach online, because I need people to call me out on my silly board mistakes. So let me see here. Yeah, so everything is set up perfectly. So I want to show you how we're going to get around the notation of the sum of these two integrals, and I want to get you to and show you how it fits into theorem 8.1. So follow me off to the left side over here, and I'm going to start with a very simple statement. Let's say the statement v is equal to v. Now, I don't think that you're going to argue too much with me about that. V equals v. But if you have a problem with the law of identity, then no problem. Okay, so let me continue. So I'm going to take the derivative of v with respect to x on both sides of this equation, but I'm going to write it in two different notations so that you see it. All right, so if I take the derivative of v with respect to x on the left side, that's the equivalent of just v prime, right? You'll give me that. I mean, just like you would tell me that f prime of x and dy dx and y prime, these are all synonyms for the derivative of a function f with respect to x. Now, at this stage, I'm going to use this Leibniz notation to bring this dx to the right side, and this is the power of this notation. So that would leave me with dv is equal to v prime dx. Now, we're almost there. So I now can substitute dv anywhere I see a v prime dx, right? So maybe you can follow me here. So right here is a v prime dx, and I'm just going to substitute. I'm going to erase these arrows in just a second. So I'm going to be substituting dv right there. And I can go through the same setup with having u equal to u, and then du dx is equal to u prime. Therefore du is equal to u prime dx. And there again, one more round of substituting. Only this time I have my u prime and my dx will become du. Okay, now these arrows are cluttering my workspace, so I'm going to erase those. But as soon as I erase these and substitute, we are basically all done. You'll see it. Okay, so just relax. I know you're on the edge of your seat right now in anticipation. I know it. I know you got 4 tabs open with your phone in your hand, and you're giving me about 30% of your attention, but that's okay. I dig that. That's okay. All right, so u prime dx is going to, so now we have v du plus, okay, we're going to integrate here, and that v prime dx is going to become, so I still got a u left in here, and that v prime dx is going to become a dv. Voila. So now, are we done? Yes, well, in a sense that we are done. The only thing is, if you let me zoom in to Theorem 8.1, and what you can notice is what they've done here is they've just rearranged the equation. Okay? So if I just simply move my integral of u with integral of u with respect to v to the left side. Now we're going to have to, you got to think about, well, I'll do this just so, I mean, operationally, you have to subtract that to get it to the other side of the equation. So bringing that over, so I got u dv, and of course this u dot v, we're going to be moving that to the right side of the equation. And again, you're going to have to change those signs in order to move them, u dot v. So right now I have negative u dot v plus the integral of v du, but you probably already see it. I'm going to be dividing by -1, dividing by -1, dividing by -1. And when I do, what you're left with is exactly what our integration by parts formula looks like in Theorem 8.1. Okay? So now you cannot say, where the heck did they come up with this stuff? Because you, if you were decently awake, decently caffeinated, you could have followed me through that. That was not that bad. So how does this work? Right? So let's get to the part where I actually show you how to do some of these, how to use this integration by parts technique. So the game and the game is as follows. So notice off to the left here, I have written 4 different parts that you have. So parts 1, 2, 3, and 4. So you have u, du, v, and dv. Now here's the important part. So what do you have control over in this integration by parts technique? Well, you have control over how you want to define u, and you have control over how you would like to define dv. Okay, do you understand what I just said? So what I just wrote, these are the parts that you have control over. All right, now once you have defined u, once you have defined dv, the consequences of that, right? These other parts are parts that you have to derive. Now look at the way I wrote derive here. You know, they say never get drunk and derive. That was a joke, by the way. You should have laughed at that, but if you didn't, maybe it just passed you by. So as a consequence of defining your u, defining your dv, the parts du and the parts v will be what you have to derive. All right, no more theory, let's get to it. So I will get back to the part of trying to explain to you how do I know which, right? So if you have to choose what you want to call u and choose what you want to call dv, I'll get back to the what's some tips for what is a good u to choose or dv to choose. But as of right now, you are just in anticipation, and I need to show you how this technique works. So example 1, we are going to integrate x multiplied by e to the x with respect to x. Okay? So at this stage, notice that I said that what you have control over is how you would like to define u and how you would like to define dv. So again, no explanation on how I knew to choose what I'm about to choose. I just want to show you the technique. So I'm going to let u be x, and I'm going to let dv be what's left, right? So I chose u to be x, so look at me. Then what's left is this e to the x dx. So I'm going to let dv be e to the x dx. Okay, now, this is not bad. Let's start with du. That'll be simple enough. So once you have defined u to be x, then a consequence of that would be the derivative of u with respect to x is, well, dx. I do hope, I tell you what, it's been a crazy week. You may forget little stuff like this. How did I know that? Okay. So if you want to take the derivative of u with respect to x, well, what's the derivative of x? I know, 1. Only, again, we're using this we're going to use that Leibniz notation that allows us to bring that dx to the other side. So that's why I'm about to erase this and write du is equal to dx, okay? All right, I'm not going to do that anymore. Well, yes, I will. I'm sure I will. Du is equal to dx. Okay, now, what's left? Well, I still need v. All right, well, let's kind of come off to the left. Let me show you how you arrive at v. So because you chose to represent or to define dv as e to the x dx, then to get back to v, we're going to have to integrate, right? Because we have dv, and if you integrate a derivative, you will return to your original function. So the way this works is we're just simply going to integrate both sides. Right? That integration of both sides is important because if you integrate let's say 1 with respect to v, you just get v. I hope that makes sense. And as of right now, I'm going to go ahead and integrate this, or I'm actually going to go ahead and leave the right-hand side of this equation alone for right now, okay? So v is equal to the integral of e to the x with respect to x. And now I know what to put here. Okay, ready? So what we need at this point, hold on, bear with me for just a second. So what we're going to need at this point is to plug everything in to our integration by parts formula. All right, so let's, I'm going to make that a little bit larger just so you can see a little bit better. All right, so let's take a look. So every single one of these parts that I'm boxing in here should be substituting. Okay, I'm going to draw you some arrows. I'm actually going to see if I can find a different color here. Let's do purple. Ready? All right, so V is going to go here. Du here. Ready? Or let's say U. It's going to go here. Did I plug in? I don't know. Yeah, U is going to go here. Oh, my apologies. Okay, U is going to go here. And what? So we have du, we have v. So v is going to go here. All right. This is actually it's actually hard for me to see this, so you have to forgive me. I'm looking to the left of my paper to make sure I can read, because I can't read that theorem very well. But if I make it larger, I don't have any place to write. So thus is the problems. Okay, so let's now go ahead and put everything in the right spot. So I'm gonna leave the left-hand side of this equation alone for just a second. Let's see if I have everything in the right spots. See if in other words, let's see if I drew the arrows correctly. So we said that it's going to be u times v. So we said u was defined to be x, and we said v was defined to be the integral. Let me go ahead and write that this way. Defined to be the integral of e to the x dx minus the integral of, and now continuing. So in this case, I think what we're going to do, I can see why this is all getting cluttered. I think it's this. Let's do it this way. I was hoping to show you before we actually take the integral of v, but this is not working out. So let's go ahead and go a little bit farther over here. So if you integrate e to the x with respect to x, then v is simply equal to e to the x, right? So I think it's going to be a whole lot better if we just rewrite v as e to the x. All right, so du was dx, and in this case, v is e to the x. All right, so I'm going to try, and I don't care if you're laughing at me. It does not bother me. I'm going to try one more time, see if I can draw these arrows. So v is going to go here, is going to go here. X is going to go, or U is going to go here. And du is going to go here. All right. So, ready? Let's finish this up. So, we have u times v. So, that's x times e to the x minus the integral of v du. So, v is e to the x, and du is dx. Beautiful. So at this stage, and don't forget I'm going to kind of give myself a little bit of space here. Don't forget the point of all of this work is because you want to find the integral of x times e to the x dx. Right, so that is what is on the left side of this equation. X times e to the x dx. Right? There would be no point in using this integration by parts technique if we had a shortcut for integrating that product of x e to the x. But notice that what we're doing is, this was a matter of breaking it up, that difficult product, breaking it up into multiple parts, and then integrating those parts to get what we have right now. So let's finish this up. So x times e to the x is just x e to the x minus, now hold on, if you integrate e to the x with respect to x, you are again going to get e to the x. Now, of course, if you were thinking, hey, you forgot that plus c when you integrated dealing with the v, it's okay because there's always going to be one last round of integration at the end. So as long as you can remember to put plus c here, everything is good. So what is the integral of x times e to the x with respect to x? Well, there it is. You got it. All right, so that is the setup. That is the integration by parts technique. So let's do another one, okay? Let's do another one, and again, I'm going to punt on giving you hints of how to know to choose u and how to know to choose dv. That'll come in just a second. So we're going to, example 2, we're going to integrate x squared ln x. So that's a product, and we don't have a quick way of integrating that. We're going to have to use a different technique, and that technique is going to be the integration by parts technique. So you know the deal. We need to define what we want to call u, and we need to define what we want to label or as dv. Okay, so in this case, we're going to let u be ln x, and we're going to let dv be what's left, right? So I'm going to erase what I'm about to write here. But you just decided that u is ln of x. So now notice what's left. What's left is an x squared dx, right? So dv would have to be x squared dx. All right, now that was the parts that you had control over. But what comes now is a consequence of those, of how you defined u and dv. So du, well, if you take the derivative of ln x with respect to x, you know that to be 1 over x dx. And here's the part, really the only part that you have to roll up your sleeves is when you're trying to figure out v. So let me take this guy, bring him off to the side. So our statement was dv is equal to x squared dx. And let's go ahead and do this. So we're going to integrate both sides. And that will tell me that v is going to be equal to x cubed over 3. And again, you can write a plus c if you want, but really that will come at the end. So we'll have one more round of integration to do. So don't worry about the plus c right now. So back over here to v. So x cubed over 3. All right. So you know the deal. We're gonna, let me see if I can bring this guy with me. Maybe I actually still have it in paste. Look at that. Look at that. I'm good. All right. So let's put everything in the right spot. So if you want to integrate x squared ln x, I'm running out of space here. So if you want to integrate x squared ln x, that was the original question after all, with respect to x, then maybe it's easier to use this parts technique. So u would be ln of x, and then we're going to place v, right? So v is going to be x cubed over 3 minus, well, we're going to have to integrate, and let's see what's in here. V, which is x cubed over 3, multiplied by du, which is 1 over x dx. All right, so what's gonna happen right now is I'm gonna go ahead and simplify this. Ln of x. Well, I'm gonna integrate this one last round of integration, and then we'll see if there's any way that we can combine or clean this up a little bit. So this is going to end up being x cubed ln of x over 3 minus, and let's see what happens here. So for sure I can cancel this x and write x squared here. So does that make sense? So at that point, I would just simply have 1/3 of x squared. And what's going to happen in just a second is I'm going to bring that 1/3 out in front of the integral, right? Because I had x cubed here, divided by x is just x squared. All right, so let's keep going. So x cubed ln of x over 3. And let's go ahead and bring that third out in front of the integral. And there's nothing left to do but some basic power rule integrals. So when all is said and done, we're going to have x cubed ln of x over 3 minus 1/3 times, well, we have, that's going to be x cubed over 3 and plus c. Be careful when you start, integration's hard, harder than derivatives, because it's like a puzzle. It's not as straightforward as derivatives. It's like you have the answer and you're trying to find what the question was. So as you start to learn some of these more advanced integration techniques, you start to forget things like, wait, did I add c, right? But if you don't put plus c, then in essence you are actually saying that you know what c is. So you would be telling me that c is equal to 0, if you forget to write plus c, which is a lie because you don't actually know that c is equal to 0. So with the c basically means it's one of an infinite amount of antiderivatives. Now, I'm going to clean the rest of this up, but at this stage, your calculus is over, right? I mean, you are just trying to appease your math teachers at this point. Or, I mean, unless you have something in mind that you would like to do with the derivative, you might want to develop that habit of factoring. But the derivative's done, okay? It's just cleaning it up to appease the people with the red markers and red pens at this stage. So that ends up being minus x cubed over 9 plus c. All right. Well, let's celebrate because we're done, because you now know how to use the integration by parts technique. So where do we go from here? So I'm going to show you some quick tips. I'm going to actually break from this video, come back, and I'm going to show you some tips for choosing a good U and a good DV. And then I'm just going to ramp it up, make it life harder on you, try to, pull down some of that self-esteem that you just built up right now by making the problems harder. See you in a few.